All right, hello everybody. Welcome to the stream. It's my second one since I've took kind of a break from streaming. I hope you're all doing well. I hope you can hear me okay. So it would be great if you could in the chat let me know if the levels are fine and if the sound is okay. And I'm just going to assume that it is, and I'm going to start talking about this thing, which we are basically all here for, I guess. So what's the point of this stream? Well, if you've been following my channel, you might have noticed that I have no content, I think, basically no content on percussion, right? So I've done a lot of videos like on all kinds of different synthesizer circuits that are like basic building blocks like VCAs, VCOs, filters, whatever, like those kinds of things. But I've never talked about percussion at all. So in this stream, basically, I want to change that. And my basic thinking is that to me, the kind of like pinnacle of percussion, synthesized percussion, is like the classic Roland drum machines. So that would be like the 808 and the 909. And I kind of feel like because they are so dominant, like in the electronic music scene, they are often mimicked and often like kind of built upon and everything. So to me, like those are the things that I want to look at first. Now the thing is with the 808 and the 909, those two machines are relatively complex, and looking into like at their schematics as a starting point, I figured might just be just too daunting. And I looked around my room and I realized, well, I have this thing here sitting on my shelf. It's not in great condition, but it does work. And it is kind of, if you will, like the little brother of the 808 and the 909. So I would love to give you more of a background on it, but honestly, I don't know too much about its history. I know that I think it was intended to be like a companion for you if you were like practicing guitar at home and you wanted to play along to drums. Then basically what you would do is you would go out, you would buy one of these and then plug it into your sound system and play with it. And it was accompanied by the TB303, the bass synthesizer, which you know, like the idea there was similar. Like the original intention was that it was like supposed to simulate playing with a real bass, and obviously it has been like those machines have been kind of like moved away from that purpose. But yeah, that was like I think the original intention, and so. This machine is, I hope I'm not angering anybody by saying this, but this machine is really, it feels really cheap, right? So it's all plastic, like all of these knob caps are not really well made. The thing is, like this particular thing is kind of falling apart. I've bought it used and the previous owners haven't kept it in great shape, and I've never like, opened it up and you know try to fix things, but yeah. So that's the thing. But also it means that the circuitry is rather simple, because if you look at the interfacing elements, you're going to notice that as opposed to the 808 and the 909, there are no kind of controls for you to like manipulate the individual voices, right? So we have 6 voices in total. We have a bass drum, we have a snare drum, we have a low tom, a high tom, we have a cymbal, and we have a hi-hat. But there are no controls that would allow you to manipulate those sounds. You can only set the volume, and that's basically it. And of course, like as a drum machine, that is not great because it doesn't allow, you know, for much flexibility. You can always like edit the sounds after you've recorded them, but in general, like it's a really limited machine. But for us, I figured that's really good, because it means, like I'm assuming, this means that the circuit, the schematics will be rather easy to read. And I think that the principles that they use in this drum machine are like basically similar to the ones that they use in the 808 and in some voices of the 909. So that's my motivation, like why I want to pick this thing out in particular. And yeah, how do we start out? Well, maybe let's first take a listen to it. So I'm gonna warn you, like I said, this thing is in pretty rough shape, so it makes noises. If I turn this up, I think you can hear it already. Maybe you can. So I think you can hear, like, every time the LED lights up, you can hear it make a noise. Right? There it is. Amazing. All right. Let's try this. All right, that's not the best pattern. Let's try another one. That's better, I guess. All right, as I said before, the only controls that we have are like to change the levels of the voices, and that's it. There's one control that I think is going to get pretty important, and that is the accent control. The accent control kind of lets you put accents at certain points, like in the sequencer. So if I select the accent here, then you can see, oh, you can see because I'm not in write mode. Now I'm in write mode. Now you can see where the accents are set. And if I turn this down, you will hear that now, like all of the sounds are like at the same level. But if I turn this up, if I turn it way up, then you can hear that now, like, individual notes are emphasized. They're louder than the other ones. And I think that's gonna be important when we look at the schematic. Now, all the other controls, I figure, are for now relatively irrelevant, because all that we really care about right now, or that I care about, is just the voices, right? So I want to know, like, how are the voices synthesized? All the control stuff, like the sequencer, the master volume, the tempo, you know, this computer controlled, whatever that means, circuitry, like, for now I don't really care about it. For now I mostly care about these voices. And now the question is, like, how do you reverse engineer something like that, right? So how do we figure out how to make a circuit that sounds like the bass drum or the snare drum or the tom or whatever? Well, normally, like, if I was an amazing engineer, maybe I could just hear the sound and then know, you know, how we could approach that. But I'm probably not. And also thankfully we have like a way easier path laid out for us, because these machines, they came with service manuals, and these service manuals are amazing because they allowed you to repair the machine. They told you, like, what the machine is, how it works, how it's set up. And if there was something broken, which, you know, with mine is actually, it would allow you to, like, go in and fix it, which is great. And for us, that means that we can just find the service manual, and that will allow us to have a look at the entire circuitry, like at the schematics, basically. And lucky for us, I've already dug that out. It's not hard to find if you want to find it yourself. I can put the link in the video description. You can also just Google it. If you Google 606 service manual, you'll find it, and it will look something like this. Right, and you can see that this is really what's the right word? In depth, right? So it explains all sorts of things. Like, first of all, it brags about, like, all the different features that it has. And then it tells you how much it weighs, what the dimensions are, the power draw. This thing right now, I'm running it on batteries, by the way. So you could run this on batteries, or you could run this with an AC adapter. And this might also be interesting for later. So we can see here that 9 volts is the AC adapter, and the batteries. Wait, 6 volts times 4? Interesting. So that would be what? 24 volts? That's a lot. Interesting. All right. Right, then you here have a nice picture of it, and it tells you, like, what they are. I'm guessing these numbers are, like, part numbers. I don't know. Which would be nice if you could just, like, go ahead and buy new ones if you break them. And then obviously you have like stuff like the connectors on the back of the box. Oh yeah, something that I didn't mention, like the drum machine has like 2 trigger outputs, which is interesting. Like they are mapped to the low and the high tom. So if you input low or high tom steps into the sequencer, then whenever they are triggered, like the drum machine will send out triggers here, which you can use to with your modular synth, for example, with another drum machine to trigger something. And then, oh yeah, true. They also have like this horrible DIN connector, which is it's basically a MIDI connector. I think they are identical. I think you can plug a MIDI cable into here, but since it's not, I think it predates MIDI, and so you cannot send MIDI signals in there. You have to use like an adapter that adapts between MIDI and then this kind of, I don't know if it's proprietary, but this standard here. So that's a drag. Like I bought this adapter to be able to like sequence this from something else. All right. Next sheet is, I think, not super interesting for us. I mean, it shows us like the different kinds of chips that they were using. Now, I'm not sure about this, but I assume that like all of these specific types of chips, like these models, I'm not sure if they're still in production. And I mean, if you're like a purist, probably you'd want to like hunt these down. I personally, I'm not sure if that's really worthwhile. So, I mean, and today, anyways, like we're just going to use the parts that I have on hand. So, but yeah, you can see they're using a NOR gate, they're using a NAND gate, they are using an op-amp chip, and this is probably, oh, this is a comparator, all right. They have a Hexmit trigger, which we know, if you've seen my VCO video, like this is what I used there. And yeah, that's probably useful for later. Next sheet, we can see, this is a block diagram, it says. So I'm guessing these are like visualizations of like how the sound flows through the machine, but that's also not super interesting for us because, as I said, for now I'm just mainly interested in the voices, not in like how they interact. This is, I am guessing, the interfacing layer, because you have a lot of switches here. And it does not look like anything that would produce sound to me. Oh, whoops. Didn't mean to do that. Right, we were here. And then after this one, this is where it gets interesting, right? Because you can see here that the different voices are labeled. So you have a bass drum here, you have a snare drum here, you have the high tom here, the low tom up here, and you have the cymbal, hi-hat, and outputs, trigger out. Yeah, so that's the interesting part. And to be able to show stuff better here on the schematic, I decided to put this on my pad. And the way that I want to do it basically is I can like draw here on this pad, and I'm hoping that you can see it. I think you can see it. And I think this way it's going to be easier to visualize, or for you to kind of like understand what I'm talking about. And the way that I want to go about this now is basically I want to pick out a voice. I think I'm going to go for the bass drum because the bass drum it looks to be the least intimidating to me. We're going to try and figure out, you know, how it's set up. Then we're going to try to replicate the voice in the circuit simulator. And once we've done that and we've really like solidified the knowledge of like how it works, then we're going to go to the breadboard and we are going to set up the circuit there, and then hope and we'll see if it works. That's the plan. I'm going to check if there are any questions so far, or rather, like if anyone has questions, then feel free to post them now. All right, someone said, can you change the color of your pen? Sure, I can do that. I can make it, let's say red maybe. That might be a good thing. Let's go for a darker red. All right, also let me know, like if the color doesn't work for you, then please tell me. Anything else? Oh yeah, the ratio of this is a bit weird because the pad has a different kind of ratio than 16:9. So the trade-off is like either I have the black bars on the side, or if I crop it to 16:9, then it's awkward because I don't know if you can see what I'm seeing on the stream, you know, because the top and the bottom would be cut off. That's not ideal. So you're gonna have to live with the black bars. I'm sorry. All right, then let's get into it. So, like I said, I did look at this schematic before, just to kind of assess like what would be the best option to go with first, and I think it's the bass drum, simply because if we look at this, we can see here that the bass drum, I think, starts kind of here. I think this is the trigger input. I'm going to make this more red. I think that's going to help. Boom. So I think this here is the trigger input. And I'm pretty sure that this over here is the bass drum output. So that would mean that the bass drum itself is this kind of chunk here. And if you compare this chunk, wait, I'm going to make my pen a bit wider. So if you compare this chunk here to the snare drum, for example, so the snare drum I think starts here, and I think the output is over here, and I'm assuming that the noise source that we see over here, right, we see noise here, noise generator, there it is. So the noise generator, I mean, that's usually how snare drums are done, right? So snare drums are usually like a mixture of like a percussive sound, like a plucky kind of sound with noise. So the snare would probably be this, all of this, right? And if we just compare like these two, I guess you can agree that the bass drum looks a lot less problematic, especially if we then look at the cymbals, right? Because for the cymbals, like, it's even more crazy, because for the cymbals, you have this section over here, which is kind of like it's like 6 oscillators that are mixed together that make like this metallic, like clangy sound. And that noise is then shaped either into the hi-hats over here or the cymbal over here. And as you can see, like, those are also way more complex than the bass drum. So that basically leaves us with the alternative of doing the high tom or the low tom. But I think, like, to me, this also looks more complex than the bass drum. So yeah, that's my reasoning for why I want to start out with a bass drum. And I haven't heard any what's the word, any complaints from your side, so I'm just going to assume that that's fine with you. All right, so with that, let's start looking at the bass drum. So let me highlight this. There's what we're looking at. The bass drum. Like I said, I am fairly certain that this part over here is the trigger input, right? This is kind of where the sequencer of the machine puts in triggers to make the bass drum go boom, basically. And why do I think that? Well, because this section over here looks very much to me like a kind of gate to trigger converter, or at least a buffer. And also this part over here looks terribly familiar. So this I've seen a bunch of times before, and I'm pretty sure it's called a bridged T network. And I've seen this used a bunch of times, like when people set up like bass drums or snare drums or toms. So this seems to be like a fairly like standard way to make percussive sounds. And since I know that this kind of building block is triggered basically just with a signal that's being fed in here, I think it's safe to assume that the part that I outlined here is a gate to trigger converter. So, oh yeah, one thing that is obviously a bit odd is that this IC over here is basically not labeled, right? So it just says IC5 and A. So it could be anything. But I'm fairly sure that it's an op amp. We could look this up, but I don't think we need to. Simply because, you know, I know that in a bridge T network they use op amps also, characteristic, you know, 2 inputs, 1 output. That seems very op ampy to me. So I think it's fair to assume this is an op amp. So knowing that, we can basically go in and say this here is going to be the non-inverting input, and this thing here is going to be the inverting input, simply because in a bridge T network, or in a bridge T, like if you use a bridge T network with an op amp, you put it like in the negative feedback path. So that will be this path, you know. Yeah, so the question now is, do we first look at the gate to trigger converter, or do we first look at the bridge T network? I think it might be interesting to first look at the gate to trigger converter, because I assume that there are some things going on there that we actually can get around, because I believe that this machine is running on a single site supply. Why do I believe that? Well, if we look around, we can see that I'm not sure why it says, I'm not sure if this is a G or what it is, but I assume that this is 15 volts. And if this had a symmetrical power supply, then we would expect to see minus 15 volts somewhere. But instead, we only see ground, right? Ground here, ground there, ground there. It's a weird symbol, but it's ground. And I don't see minus 15 volts anywhere. So that would probably mean that they needed to do like some trickery to like be able to work with op amps properly, you know, like to bias stuff upwards. And why do I think that? Well, maybe we start at the beginning here. So if we go back to the trigger input over here, right? So let's assume that from here we get a signal that looks like this, right? This comes in over here. And then we can kind of trace the path and see like how it gets to the op amp. So the first thing it's going to pass is going to be, make this a little bit smaller, is going to be this section here, which you probably all know and recognize as a voltage divider. And the values are kind of interesting. So we see that we have 22K here, and then we have 10K to ground. So this is, I can't do math in my head, but I would assume that if we have 1 volt over here, then we would have at this point, it's gonna be less than 50%. So I would say something like, well, maybe 0.3, something like that, volts here. So we are scaling it down basically, right? Oh, I'm seeing at in the chat that you're talking about the rails. This plus 15F, so it's probably 15 volt rails. Where did you see F? I didn't see F anywhere. Oh, here, right? This is plus 15F. All right. So what do you think that means? There's also plus 15. Oh, these are just input voltage nodes, I would assume. Right. Okay, so maybe the F and the G, it just refers to like positions on the board or whatever. That's what I would assume, but I think we can safely assume that it's 15 volts. All right, so someone just said it's 33%. Good. So my assumption was actually not that far off, right? So we're probably not going to get a 1 volt pulse, so it's going to be probably going to be higher, right? So it's going to be, I don't know. It would be a good question, like what kind of voltages we get here. But okay, so we can hold we can put this in here. We know that this is 1/3. And then basically what happens is we have a voltage pulse that comes in. It is divided down with this divider. And then here we have a very basic NPN transistor. NPN transistors, as we probably all know, work like this. So whenever the voltage at this node here goes above around 600 millivolts, then the transistor will turn on and it will allow for current to flow in this direction, right? Into the collector and out of the emitter into ground. Right, so then for us, this thing down here is not interesting because, you know, the current just disappears, so that's fine, that current's flowing down. So for us interesting is the part that is above the transistor. And above the transistor is a little bit of a mystery. So normally, like in a normal kind of buffer like this, I would assume that this node up here would be connected to the positive rail, right? Because normally, to me, it seems like, okay, so we have a trigger coming in this way. And then we want to have like a buffered, amplified, whatever version of it, basically over here. But in our case, like I said, this point up here is not connected to the power supply, but instead it is connected to, well, first of all, here. But this is outgoing, right? We can see here that this is triggering another transistor, and that thing is like going away from here. It's going all the way over here. Whoops. And it's going in here. And we can see that this is somehow related to the trigger output. So probably not really what we're looking for. Like this is not the source, right? This is just like something that is also looking at the signal. So that's kind of a dead end. So we have to follow this line further down. We want to know like where it's actually coming from, right? So if we follow this down and we go further and further and further, we can see that here it is going into this subboard, which houses the toms. But we can see here that this kind of looks like vaguely like the structure that we have at the bass drum, right? So I think this is also just consuming whatever signal there is, right? And then if we go further down, we can see that here we actually have an input, right? So here we actually have the trig flag. And that to me is a little bit weirdly named because I think that all of these flags are already triggers, right? So what is this? Well, I think it has to do with the accent. So my assumption is simply because it seems to be going to all the voices, right? We can see here that it's being used in exactly the same way as it is for the bass drum over here. And this is the symbol. And then also we're going away from here and we are ending up over here. And this again seems to be a very similar structure. And this is the open hi-hat, and same thing down here, closed hi-hat. So I assume, like my assumption is that from this point here, from this trig flag, we get a kind of constant voltage that changes depending on whether there is a trigger set on the current step and, like, you know, how loud is the accent setting. Basically, that's my assumption. And also my assumption would be that if there's no trigger set, then this would still be outputting a kind of like default voltage. And I make that assumption because I did previously build the 808's kick drum on stripboard. Like this was years back. And I remember that I had this problem that I had like a trigger input and like another input, and the module would only work when both inputs would get a voltage, right? Like one of them would have to get a trigger and the other one would have to get a constant voltage. And to me, this seems plausible because if you now go back up here, then we can see that if that is the case, then here we would have a kind of mystery voltage, right? This could be basically anything. And this could be any voltage. It could be 5 volts, 6 volts, 10 volts, whatever. And if that's the case, right? So let's assume for now, like we're just gonna assume that this is, let's say, 5 volts, right? So if this node here was sitting at 5 volts, then we can kind of like continue our investigation of this section. So as we established earlier, when we now get a trigger into the bass drum input, then this transistor here will be activated. We will see a current flowing down through the transistor, and the origin of that current is this 5 volts node up here, right? And so then what happens is, well, for one, obviously current flows in this direction. We've established that already. But also we have another voltage divider here. We have 47K, 10K. That should be about 15%. I'm bad. Like, please calculate it for me. But I'm gonna go with for now, like let's say 2/10. Wait, 2/10 is 1/5. Doesn't really matter, right? So 1/5. We're just gonna say. All right. So the situation is that before current flows through the transistor, the voltage at this node will be 5 volts, right? Because if no current is flowing down, then the voltage here is identical to the voltage that is up here. Now, as soon as this transistor opens up, the voltage will drop, right? Because this is a voltage divider. Now, this node here will almost sit at ground level, right? So then, if the voltage here drops down here, then the voltage here must also drop, right? Okay, I'm gonna clear this up to not overcrowd this, right? So the assumption now is that the initial state is that this node is at 5 volts. Oops, I can't read that. 5 volts. And then once this thing gets activated, the voltage here will drop to a much lower value, something like 1 volt, I'm going to say, maybe less. All right, so that means that this transistor over here will be affected, right? This is a PNP transistor. This is the twin brother of the NPN, but it's like everything is inverted. So basically here the idea is that as long as the voltage at this node is high, the transistor will block, because the PNP will only allow current to flow in this direction if current can also flow in this direction, right? But in our initial state, let's go back to that, the voltage over here would be 5, the voltage over here would also be 5, and so that means that current cannot flow in this direction here, so from the top to this node, simply because the voltages are the same, right? We have 5 volts here, we have 5 volts there, so current cannot flow. But then, if the voltage here drops, right? If we drop down to 1 volt here, then all of a sudden, current can flow and will flow through the transistor and here and to this node, and this will allow for current to flow in this direction. All right, so that's the mechanism, right? Trigger goes in, this transistor opens up, this transistor opens up, and current flows in this direction. Okay. So then what happens is that before this transistor here starts to open up, the voltage at this node will be 0, right? Because we have ground down here. This connection is cut off, and so we have 0 volts over here. But then as soon as the trigger comes in and both transistors open up, we will have a voltage over here, and it's gonna be fairly small, right? In our case, when we have 5 volts up here, we have a 10K and a 1K resistor. So that should leave us with, in our case, 1/10 of 5 volts. So that would be 0.5 volts, I guess. 0.5 volts at this node. All right, interesting. Does anybody have a question? I think I see something in the chat. This is a high gain switch circuit, which is integrated at C25. Yes. All right, the X and trigger line is both a variable level and trigger pulse together. Yeah, that's what I assumed. All right, cool. Good. So as we saw, basically what happens is just that the trigger that we feed into here kind of materializes another trigger at this node, right? And then what happens, and this is what I meant earlier when I said that they did some trickery, like to get the op-amp to work with a single supply, is that they first, up here, they take the supply voltage, 15 volts, they filter it, so they have a 10K here, and then they have a capacitor here, which I think is a 47 microfarads. Like, this is a bit annoying, like that this schematic does not specify what's the word? The denomination? Is that the word? I don't know. So we don't know if this is nanofarads, microfarads, whatever. I think it's microfarads. Right, so I assume that this is a 47 microfarads capacitor, and if it is, then I'm pretty sure that this setup is to filter out low frequency noise, right? Because as I said, this is a low pass filter, right? It's a voltage source followed by a resistor followed by a capacitor to ground. That's a low pass filter. And since the 47 microfarads is like really big, the frequency is going to be really low. All right, and I assume that they use that to filter out like a low frequency hum, like say 50, 60 hertz, like the typical hum that you get, you know, from your outlet in the wall. Right, and assuming that that's the case over here, then what happens is that we get a stable 15 volts, if you will, and this stable 15 volts we then use over here. And we, again, we divide it down, right? We have a 22K, 47K voltage divider because, you know, this is coming from 15 volts. This is going to ground. So this node is going to sit at, don't want to lie, it's not 50%. It's more than 50% because the resistance here is higher than the resistance here. So I'm going to say probably we're going to have like something around like 9 to 10 volts, 9 volts, 10 volts maybe. We can verify this in the simulator in a second. Yes, so that would be my assumption, that we have like around 10 volts at this point. And then we have a capacitor over here. And then, as I said before, we have the buffered kind of gate appearing over here. And then what will happen is when the voltage here rises, it will kind of push against this capacitor, which will mean that the voltage here will rise. Let me clear this for a second. All right, so we have first state, second state, right? Low, high. Hope you can see that. When it goes high, it pushes into the capacitor, and this will mean that the 10 volts that I'm guessing it has will rise, the 10.5 volts. And then on the other hand, when this signal up here drops down again like this, then it will take the voltage here away. That means that this can kind of expand in this direction again. And this means that the voltage over here will drop below 10 volts, I guess. Boom. All right. Seymour asks, wouldn't R52 and R51 sum, making the voltage divider 32K, 47K? Wait, 52. And then, oh yeah, you're right. They would sum. That's completely true. Yes. So the voltage here will be lower than 10 volts, right? It's going to be closer to something like 8, maybe. All right, but as I said, I think we can verify this in the simulator in a second. Okay, Hootie dude 420 asks, is this a Japanese schematic? Do they use the American resistor symbol? I mean, Roland is a Japanese company, so I would assume that this is how they drew schematics back in the day in Japan. So yes. HG playing says the filter is a 1 Hertz filter. All right, interesting. But I mean, it does, like, you know, that's not like a solid cutoff, right? Like, it's going to affect frequencies above that. So yeah. George asks, so C18 is a DC cap and C25 is an AC cap. Well, C18 I think is polarized, right? Because it has like the plus symbol over here. And then which other one that you asked about? 25 down here. I think this is also polarized, but this is confusing to me because oh no, it's actually correct, right? We established that the voltage here is probably not going to be like more than maybe 2-3 volts max, and the voltage here is going to wobble around the 8 volts line. So I think it's correct that this would always be higher than the voltage on this other side. So I think that's probably fine. All right, let me get rid of all this. More questions. Buck asks, is that the symbol for a tantalum cap? That's a very good question. I have no idea, to be honest. Actually, I'm kind of at a loss, like what tantalum is actually good for. I used it in my power supply, but I only did that because I saw somewhere that people recommended you do it, but I have no idea why I did that. So, all right. Let's keep on going. So we've established that the trigger that's coming in over here is going to be kind of, well, the funny thing is, like, it doesn't feel like it's being amplified by this section, right? It feels like rather it's just buffered. That's how it feels to me. Right. So it's kind of buffered by this section. And then we add an offset voltage to it at this point. So we bias it upwards. And then we feed it into our op-amp over here, right? Okay, so the question now is, and I need your opinion here, like, do you want to set this triggering circuit up in the simulator and like kind of verify the assumptions, or do you think that's not really interesting? Do you want to continue with the actual sound generating thing? I'm going to give you a few minutes to, no, seconds to answer. In the meantime, we can already look a bit further ahead, but it seems to be pretty straightforward, right? So we have the triggering part, which is like semi-complex, and then we seem to have like two of these bridged T op-amp things that are, as I assume, generating the actual percussive sounds, right? Because you can see the trigger is being fed into this one, and then it's also being fed into that one, and then they are kind of mixed together over here, right? And then here, that's already the output of the bass drum part. So that seems to be straightforward. All right. Fuzzy says, do the trigger in the simulation, verify the assumptions, set it up, analyze it, setting it up, checking assumptions. All right, so you want to go for the simulator. Cool. I hope that I can do this rather quickly. Well, for the software, like for anybody that doesn't know or hasn't been in a previous stream, I use this online tool called Feldstat or Circuit.js. This is a circuit simulator that runs in the browser, which I really like, simply because you can take it with you anywhere, basically, right? So, well, you can export your circuits as links, and those links you can just open on any kind of device, and it will take you into the simulator, and you can just like pick it up and move ahead. And that to me is like really cool. You don't have to install anything. You don't have to set anything up. The downside obviously is like it's a JavaScript it's a JavaScript application, so performance isn't great, but I still really like the simulator. All right, so let's kind of move ahead. So I'm gonna, like, I can see the schematics on my pad. You can see it, but I guess you're gonna have to trust me that I am actually replicating it faithfully. So let's start. So we wanna begin with a transistor, and oh no, we have to start with the voltage divider, right? So we have the 22K here. We have the 10K over here. Let me set up the values, and then the 10K over here. And then the emitter is connected to ground. And the collector is connected to a 10K. And then we have a 47K that goes up here. And then for now, I'm just going to, use a static voltage here. Let's go with 5 volts because that's what I've used before. All right, then we have a PNP that is set up over here, connected to this divider, and it's also connected to the same. Whoops! Oh no, it's also connected to the same voltage source. Oh God! All right, boom. And then it has the divider like down here. And this also goes to ground. This is a 10K. And then this thing over here is a 1K. Then we have our capacitor. Oh, it's not a capacitor. This is a capacitor. And this is a 417 nanofarads. And then we have a resistor going to ground over here. That's a 47K. We have a 22K up here. Boom. And then we have our 15 volts. Whoops. Up here. Those are, like as I said before, those are low pass filtered. I mean, for our simulation, it doesn't really matter, but just so you can see that I wasn't making stuff up, I'm still going to set it up, and we're going to see that it's not going to add much to our circuit because obviously, like, this voltage source within Falstart within the simulator is kind of ideal, so it's not going to have any noise in it. All right. Now, if we run it, we can see. Well, this would be the initial state, right? So if I connect this straight to ground, then we can see, or we can verify that what I said is correct, right? So ground through a voltage divider is still going to be ground, right? Because 0 divided by anything is still 0. Then we have our transistor here, which is currently off, so it doesn't allow for current to flow down here. We have this PNP transistor up here, which is also in the off state because the voltage at this node is high. And so no current can flow on this path. And so the voltage over here is also going to be, well, it's very close to 0. Simply because, there's no connection up here, there's ground over here, so this is going to be 0. And then over here, we can see that this node is sitting at, oh, it's rising. Interesting. Why is it rising? Oh, it's rising because this capacitor is filling up. All right, let's speed this up. Right, so that would actually be the filtering action, right? Because the capacitor is like slowly filling up, and then it's going to be like this reservoir. Like whenever there's going to be a fluctuation in here, it's going to be like a separate kind of source of current. All right, this really takes long. I think now it's where it's going to be 13 volts. Interesting. All right, let's turn this down. Okay, so the voltage over here, 9 volts. So I didn't guess that badly. And over here 0. All right. So then we want to add an output over here. And we can view this in the oscilloscope, and as we can see, this is like steadily sitting at 9 volts. And now I'm going to replace this ground here with a with a trigger, so with an AC signal. For now it's 5 volts. I guess 40 hertz is fine. All right, we can see basically that my assumption was correct. So we see that the voltage at this node over here is kind of jumping between 9.2 and 8.6 volts. So the center is like kind of in the middle, you know, around 9 volts. And then we're just going above and below that. Oh, wait, that's the problem. I chose AC. I wanted to choose like a pulse. Cool. So that should be more accurate to what's actually going on. All right, but it still looks very similar, right? You can see when the trigger goes high, then you can see that the voltage at this node will also go higher, like above 9 volts. And then when it's returning, when the pulse is returning to the low state, again it goes low. And then you can see like this very like long drawn out, like how it goes back up to 9 volts. I'm not sure if that's significant. I would assume that it's probably not, because with triggers we only care about rising and falling edges, like steep rising and falling edges. So I think this is what we care about, like this stuff here. But this is still interesting to me, because it's like they went through a lot of trouble to like have it there, right? Let's try to play around with this one. Let's bump this up to 10 volts maybe. Let's see what happens. All right. So as expected, now the outcome, like the trigger that we get, is like peaking at a higher point, right? Previously it was at like 9.2, now it's at 9.7 volts. If we drop this back down to 5, you can probably see this. You can pause it over here. Boom. All right, so you can see that here, like this trigger is like much bigger than the one over here. But interestingly, I mean, it's still not like peak to peak. This is like 1 volt now. So like if the accent is set to 10 volts, we get like about 1 volt out here. Interesting. All right. Let me see if you have any questions about this. Rise and fall time is fast. The trigger in is a 1 millisecond spike. All right. What happens if you increase the duty cycle, since we won't have time to go back to 9 volts? Let's try it. Let's try to increase the duty cycle. Let's go to 50. Oh, that didn't work. Oh, I have to apply it. Oh, I have to run it, right? Otherwise it won't apply. Right now it's at 50, I think. All right. That does look very similar to what we had before, right? We're also peaking at 9.2, and this is also peaking at 9.6. So yeah, I think the outcome is basically the same. If you want to know more about this, let me know. But I think it's pretty straightforward. If we really shorten this, yeah, then we can see that it's really just it's just a very quick pulse that's coming in. And as Buck just said in the chat, like 1 volt is still a lot, since we're going into an op-amp, right? All right, so that means that our assumption was correct. We have, as the outcome, we have a trigger signal that is biased upwards. It's swinging around 9 volts. And yeah, that's basically it about this part. Then now let's go back and let's look at the actual oscillator, right? Yeah, true. 40 hertz is a pretty quick trigger frequency. The problem is, if I want to dial it down, like if I want to go down to like 1 hertz, which still is pretty fast, then the problem is that I would have to like speed up the simulator so much that it stresses my machine, and then it would just be like a slideshow. So that is not that's not a great idea. All right, debouncing. I see that mentioned in the chat. Is the trigger debounced before input here, or is the circuit debouncing maybe? Barbarossa says it's already debounced by several resistors to ground and a lack of mechanical switches. I tend to agree. I think that Well, I mean, over here, like with this transistor, like wait, no, debouncing is about if you have like multiple hits in series, right? I was thinking about noise protection, because this we have, right? Because this this divider here means that the signal has to be like big enough to actually activate the transistor. So we at least have the noise protection. I'm guessing debouncing is probably also in there. Let's hope for it. All right, now let's look at the actual part that makes a noise, or I assume that it makes a noise, right? So as we said before, I think this is the non-inverting input of the op-amp, and this is the inverting input of the op-amp, and this is obviously the output. Yeah, let's look at this. This is rather daunting, right? Because like normally you see in a circuit, you see an op-amp set up as a buffer, right? And if you just have a buffer, you just have this nice and friendly little setup, right? This is not intimidating. This thing up here is pretty intimidating, but in general, like it's a very similar concept, right? Because you can see here that in the buffer, you also have a signal applied to the non-inverting input, and then you have a feedback path here that goes back to the output. Now with a buffer, it's very, very simple, right? Because you just want to replicate whatever voltage you feed in here is the voltage you want to get out here. And the way that works is you simply connect the output to the inverting input, and because of how the op-amp works internally, this will result in a situation where the voltage here is the same voltage as the voltage here, and the same voltage as the voltage here. If you want me to go into that in detail, I can do it. I'm just going to assume that most of you probably know how this feedback loop works. If you need more information on that, let me know in the chat, but I'm going to assume that you know that. And the basis for this is basically that the op-amp, I don't like that, this kind of like humanization, but that the op-amp wants to keep its two input voltages the same. That's like an abstraction that you can put on top of it, right? And knowing this, like with this kind of abstraction, we can hopefully look at this circuit, right? So let me think about how we're going to approach this. So let's start with the kind of what's the word? With the kind of state 0, right? Let's assume that the voltage at this node is going to be 0. Then we know that in order for this op-amp to be like in a state of balance, the voltage at this node also has to be 0, right? All right. Now the question is like how do we achieve that? Like, what does the output need to be at in order for this situation to occur, right? We can probably just follow this path, right? If we go up here and we go to this node, we can see that in this direction we have a capacitor in the way. Now, assuming that this node, the output starts out at 0 volts, then that would mean that there cannot be any charge in this capacitor, simply because there's no voltage source anywhere up here, right? Because we have ground here, and then the only point from which current could have flown into the capacitor is actually from the output, right? So I think it's safe to assume that this cap is empty, this cap is empty, and that basically nothing is moving. So in that case, we basically know that this is going to be the state 0, right? 0 volts here, 0 volts here, 0 volts here. That's it. Boom. Right. So that's helpful because now we know like what we start out with. Now what we're going to assume is that the voltage at the non-inverting input is going to spike, right? And in our case, oh, wait a second, I'm stupid, right? This was not correct. We know that the voltage at this node is not 0, right? We just established that we have through here, we have this kind of like biasing thing, right? So the voltage here is going to be 9 volts, right? So we know that we have 9 volts over here, and that means that we need 9 volts over here. Okay, good. Sorry. Okay, so now we got to ask ourselves, like, how do we get there, right? How do we get to 9 volts up there? My assumption is that this is probably going to happen if this also sits at 9 volts. Because if the output is at 9 volts, what will happen is that we have a current that flows into this capacitor, fills it up. And that means that we have a current flowing here to this node. And in part, no, I think it's not going to flow into this capacitor. Why not? Well, because we also have 9 volts coming from here. And, you know, as long as voltage is not transformed into current, it does not kind of decline, right? So we have 9 volts all the way to this point, right? So if we also have 9 volts over here, then current will not flow in this direction, or will not flow into that other capacitor, because the other capacitor has no room to expand into, basically. And so all that happens here is that as current flows into this cap, it's pushed out the other side and it's pushed through this resistor into ground, basically. But yeah, so I assume that we're going to just like start out with a situation, with a balanced situation where we just have 9 volts here, 9 volts here, 9 volts here. That's it. Boom. Okay, one second. Chat thinks R62 is 4.7K. R62. Where's R62? 64. Oh, you're right. This is a point. That's true. All right, we're gonna go back to the simulator in a second. All right. So I assume that this is the state 0, right? We're gonna start out with 9 volts at all these nodes. Right. And then what happens is, as we saw before, that we will get a voltage spike coming in here. So let's think about what happens if we get a spike in voltage. So we're going to assume that we get our spike, and this means that initially the voltage here is still going to be at 9 volts, right? Because that's where it was previously. And so what will happen now, if the voltage here goes high, since this is an op-amp, it will subtract the voltage here from the voltage here, right? We know that this is going to be the voltage here, the spike is going to be above 9 volts, right? So if it takes a voltage that's higher than 9 and subtracts 9 from it, the result would be positive, and this means that the output is going to get bumped in voltage, right? So we can assume that the spike that we feed in here is going to result in a spike that's coming out of here. Okay, so if we get a spike that's coming out of the op-amp's output, then what I assume will be happening, since this is a really big resistor, right, 680K, then what I assume will be happening is that we push more current into the capacitor, right, because that's like the path of least resistance, simply because the resistance here is really high and the capacitor on the other side has ground, right, because it has a connection to ground here. So then what will happen is that we will see more current flowing out of this capacitor, and now the question is, does it flow to ground directly, or does it flow into the other cap? I would assume that we probably only get like really some action if it flows into the other cap, right? And if it does flow into the other cap, which we can now just assume, then the voltage here would spike, right? The voltage here would go up. All right, you know what? Like this, I feel like this entire thing is like so complex that probably it's going to be easier if we just set it up in the simulator and kind of watch what happens there, and then we can maybe get a better picture of it. Sorry. All right, let me switch over. All right. Okay. I am going to set this up over here. I'm going to do it for now independent of our triggering circuit. All right, so we have a connection going up here. We have a 56 nanofarad capacitor. We have a 3.3K to ground. Maybe we need a little bit more room over here. Boom, like that. 3K3. Oh, sorry. 3K3, and then another 50. Oh man, another 56 nanofarads capacitor. And then we go back to the inverting input. And then we have our huge resistor up here, which is a 680K. And now we are going to just verify the assumption that this is that the state 0 is like as I expected it would look like, right? So we apply 9 volts, and then we can see that after some weirdness, the voltage at the inverting input is going up to 9 volts. The output voltage is, oh, it's actually oscillating. Interesting. All right, let's set up an output over here. Boom. All right, let's get rid of the trigger for now. All right, so we can see that we have like a very slow sine wave oscillation. Now, I mean, keep in mind that the rate at which the simulator runs is like very slow. So this is probably not as low frequencies as you might assume, I think. But it does seem to be going down in amplitude. If we speed it up, and we can see it like stabilize. Oh yeah, now it seems to be stabilizing at 9 volts. All right, so in the end, it turns out I wasn't wrong, right? So we're going to reach a situation where let me mark the voltage here too. So that's the voltage at the inverting input. So and this is also going to be handy if we show the voltage, right? So you know, as I said, we get to a situation where both inputs are at 9 volts and the output is at 9 volts, and that's it. But as we saw before, like this whole setup seems to be kind of astable, right? So now the question is, what happens if we feed it a pulse? Oh, not a sawtooth, a pulse. And we're going to pick a very short duty cycle. All right. That's strange. I wonder if maybe... Oh, the pulse that I'm feeding is also ginormous, right? I'm feeding it like plus minus 9 volts. And the one that we saw earlier is much smaller. It has like a DC offset at 9 volts, and it's like half a volt in width. So let's try that. That's interesting. Oh, I think the duty cycle might be too. What the hell is up with the duty cycle? Oh, right. Okay, now we're at 9 volts, and then when do we get the trigger? We don't get the trigger. That was the trigger. Oh, all right. So, okay, so we're triggering so frequently now that we're actually not allowing it to like properly oscillate. So we're going to have to do this way less often. All right, let's go down to 1 Hertz. Okay, so we can see that it does seem to be oscillating slowly, and then it kind of like peters out and it like kind of like stabilizes at 9 volts. And then every time a trigger hits, which should be any second now, I hope. Come on. That's what I meant earlier, right? You pull it down to 1 Hertz and it takes forever for the next pulse to come. Let's speed this up a bit. Boom, that's the trigger. All right. And then it seems to like oscillate in response to that trigger pulse, right? All right. Let's look at the voltage at the inverting input. All right, we need a trigger, come on. Oh, wait a second, I have a good idea. We can, instead of doing this, we can simply set up a push switch. No, yeah, push switch is good. And then I'm not gonna go with 9 volts for now because we don't, like our op amp is, has like a dual power supply, right? So it doesn't, it can go below 0 volts, so it's fine if I don't bias our trigger upwards. So I'm gonna do like a 1 volt trigger here. Right, now I can trigger it manually, which is nice. So I'm gonna reset it and I'm gonna trigger it, boom. All right, so we can see that the op amp seems to be struggling to reach the state of balance, right? So it seems to be over and undershooting as it's trying to get the voltage at the inverting input to the same level as the voltage at the non-inverting input. Let's try this again. So basically, we give it the trigger, the output goes high, and then it looks like as it's filling up this capacitor, like this first 56 nano, the voltage at the non-inverting input seems to be rising with a delay, right? And so that's why it seems to be overshooting, and then it's again trying to go in the other direction. It's going negative, and that seems to be like the kind of thing that's happening here. Now the question is like, how exactly does it work? So let's maybe go back. Or maybe we can do it like here in the schematic in the simulator. So my initial assumption was if the trigger comes in over here, that means that the voltage at the output will spike. That means that current will flow into this capacitor, right? It will push current into the capacitor, current will flow out the other end. And since we have a resistor here, like if we didn't have, I assume that if we didn't have a resistor here, we probably wouldn't see an oscillation, right? So let's test that. I'm going to give it a trigger. Well, I guess you can call this an oscillation, but I guess it's so fast that you probably wouldn't hear it. But yeah, what I assume happens is current flows into the capacitor, current flows out the other end and straight to ground, basically, right? Because there's no, like in this scenario, there's no reason for the voltage to actually flow into the other capacitor. Like it's just going to go straight to ground because electricity always takes the path of least resistance, right? So it basically just flows through the cap. And then we also have this resistor over here, right? So we're going to have a much smaller current that flows through this resistor and into this capacitor, right? Like a very small current is probably going to flow through here and into this cap. I think we can verify this if we do that. Then we should see, yes, that's exactly what happens, right? The current flows through the top resistor into the other side of that capacitor, and then the voltage is equalized. So we have 1 volt at both inputs and the output, and that's it. All right, now if we put the cap back in and we do the same thing. Interesting. All right. So what I think happens is that this cap will fill up much more quickly, right? Because there's no resistor between it and ground. So it will just fill up straight up. And why is it going crazy here? That's strange. This is 0 volts. This is 0 volts. But it thinks that there's like 2 amps flowing. What the fuck? That's strange. Okay, anyways, so yes, so this cap fills up quickly, this cap fills up very slowly, right? If we put the resistor here back in, this was a 3K3. Come on. All right, so now the same thing still holds true, right? If the trigger goes high, the output voltage goes high in an attempt to get the inverting input also up to the same voltage as we have over here. So we're going to have a current, a large current flowing into this cap, and we have a very small current flowing into the other cap. And so as this fills up, less and less current is going to flow into this one. More current is going to, not more current, the same amount of current is going to flow into this one. And so this cap will be charged up much quicker than this one, right? But we need to charge this cap to the same level as the other one in order to get to the state of balance, right? Because the state of balance, we only get there if we have 1 volt at the inverting input. So it's charging this one. And then what happens? Let's try pushing on this one. All right, as I said, it's and now it's going the other direction. Interesting. Why? All right. Left-hand side gets charged. Left-hand side gets drained. Okay, I understand why the left-hand side gets charged with a delay, but why does it turn around? That's the question that I have. So current flows in here, current flows in here. All right, so in order for the op-amp to go, for the output to go negative, the voltage here needs to be higher than the voltage over here, right? Because the op-amp is subtracting the voltage here from the voltage over here. So the outcome of that can only be negative if this is bigger than the voltage on this side. So why would it go higher than on this side? That's the question, right? And I think it does, we should be able to see that it does go higher. It goes up to 1 volt. And then it flips to negative. And then it flips to positive again. Interesting. Does anyone in the chat have any idea, maybe? Set the vertical scope scaling manually to prevent rescaling. And that's a good idea. I'm going to do that. Disable this. All right. That's a good trick. All right. Does anyone have any ideas why it goes negative? Why does it turn around? Okay, Buck says it goes higher than its input because it has a high supply voltage and it's using its might to accomplish its goal of equalizing inputs. Not sure I understand that. Antonio says when positive input goes low, the negative input is actually higher because it's been charging up. Well, but right now, like, I mean, yeah, if we did have a trigger, it would do that. But right now I'm like holding down the button, right? So the trigger does stay high. But yeah, I guess maybe we can ignore that. Maybe that's just like a quirk of the simulator. We can maybe maybe mark it as that. And in that case, like, okay, so then let's think about the trigger situation again, right? So I click the button, voltage goes high. This one charges up quickly. This one charges up slowly. So as this charges up very slowly, or while this is charging up, the voltage here drops, right? Because I'm taking my finger off the button. So that means that now the voltage here is lower than this one again. So this means that the output goes negative, right? Because 0 minus, this is actually not connected to ground, it should be, boom, just for correctness sake. All right, so I take my finger off the button, this goes down to 0, and then the voltage at the inverting input is higher than the voltage at the non-inverting input, and that means that we get a negative voltage over here. So then it's like discharging it, right? So it's discharging this one very quickly. And then it's discharging the other capacitor very slowly. I think, I've been neglecting the fact that these are connected here in the middle, right? So this is going to have an effect, correct? Because as this thing is charging up, we're going to have a voltage at this point, right? Because there's a resistor here, we push current through this resistor, so we're gonna see a voltage here, right? Because this thing is basically a high-pass filter, so we are going to see a spike in voltage at this side. All right. Okay. So as this one charges up, the voltage here is going to drop. Let's look at that. Analog output. Boom. Let's set up another scope. Right. So the voltage at this point, I'm theorizing, is going to see a quick spike and then it's going to decline, right? That's what you see over there. Right, and that's because, as I said, like as this capacitor, as this capacitor fills up, we first get like a voltage spike here, and then it drops off because as it fills up, less and less current is flowing through it, and that's why the voltage here is going to drop above the resistor. And this is going to have an effect on this guy, right? Because if initially the voltage here is high, then at that moment we cannot fill up this capacitor because there's no room for it to expand into, if you will, right? So we have a voltage here, so we cannot push current into it from this side. So that like further delays the charging process of this guy. And but you know, as this one charges up, this one is also allowed to charge up. So we slowly charge it. The voltage here goes higher and higher. We kill the trigger. We go back to 0 volts. The voltage here drops or goes negative. This thing is discharged. This means that the voltage here is going to drop. I'm guessing. Pretty sure it is. Wait, let's check that out. Let's see. So boom, we go high and then we go low. Yes. Yes, so the voltage here goes low. And then this means that the voltage on this side will also drop, right? The voltage on the this is really confusing. All right. It's making my brain hurt. I think maybe we should just build this and see how it sounds. Maybe that's actually the way out of this conundrum. All right. One more thing that I think is interesting here. I think we saw this already, like earlier when I removed the resistor. I think the frequency of this oscillation is very much tied to the value of this resistor, right? So if we increase this, let's say we go up to 10K, then my assumption is that we get a slower oscillation. And I think that was true, right? Let's speed this up. Yeah, that seems to be very slow. And now let's reduce the size of this of this resistor. Right, and then we see that it speeds up instantly. All right, and if we reduce it even more, it gets even quicker. And if we increase it again, it goes much slower. Okay. All right. Let me check the chat if there was any Anything else anyone said? Electronics is easy until it starts oscillating. That's probably true. DSP. Yeah, we could program this, but I think this is more fun. All right, so we saw that the frequency of this oscillation is heavily tied to this this resistor value, right? Because somehow, like, I can't explain it in detail now, but somehow, like, the whole situation is like tied to the fact, or is tied to the rate at which this cap is charged and discharged. Basically, the faster we can charge and discharge this cap, the faster it's going to oscillate, basically. And you know, the high level assumption is just that it's all about the way that this cap can be charged and discharged, and those two things seem to be kind of like tied together between these two caps. And I'm going to leave it at that for now. So now let's try and set this part here up on the breadboard, and let's just see how it sounds. I think that's like maybe a welcome distraction for now. So I'm going to switch over to the breadboard cam. Let me get this out of the way, and I am going to set up my breadboard. And I think I might want to get the camera a little bit closer so that you can see properly. All right, let me bring up the schematic. Okay, so I'm afraid that I probably don't have 56 nanofarad capacitors. So I think we'll have to try and make do with the closest match that I have, which is 33 nanofarad capacitors, these guys. So we're just going to try and see how they sound. Oh, and yeah, I said this before, but since I will be using a dual power supply, I have a bench power supply. I don't think we need to do like this biasing. I think we can trigger the thing with just like a regular voltage pulse. Like, we don't have to do any biasing or any insane things, which is nice. All right, let's set up the power supply. So I normally do a negative down here, and then positive up here. And then I will do ground. Wait, let me turn this around. Oh no, that's the same. Ah, okay, like this. All right, so negative down here. I hate this about breadboards. It's like, you know, they're made for single-sided power supplies, and every time you want to do dual power supply, you're gonna have to endure the fact that the labeling is off. All right, ground goes in here. Good. Okay, so first up, we're gonna need an op amp. I think I saw one around here earlier. Maybe this one is an op amp. This is 4017. I think this guy. Yes, that, I don't know if you can see that. That's a TL074. Boom. Okay. We have to go like this because with these chips, if you don't know, that's a quad op amp, so it contains 4 op amps in a single chip. These have their positive supply pin, which is like the one in the middle on the left-hand side, and the negative supply voltage pin on the right-hand side. So here. So, you know, because I have the positive rail up here, the negative rail down here, I set it up like this so I can easily connect it to the power supply. All right. Let me set up the power connections. So positive. I'm going to put down the mic. All right. Positive goes up here. And negative goes down here. Oh yeah, no worries. I haven't turned the power supply on. I've learned my lesson. Like so many people complain in the videos when I operate on the circuit while the supply is still on. So I do my best to not do that. All right. So we can pick any of the op amps. Obviously, it doesn't matter which one we pick. I'm gonna go with the one down here, bottom left. And so first of all, we want to probably set up the capacitors. So I am going to do it like, it's not going to be pretty because I don't have the time to be to do it in a pretty way. So we're going to set them up over here. We want to connect them. We want to connect them in the middle, basically. So whoops. So where one ends, the next one should start like this. And then in the middle, we want to connect the middle pin to ground through a resistor. Now in the schematic, it is a 3K3. Since we have smaller capacitors, I think to get like roughly the same pitch, I would assume that we have to increase the amount of resistance. So I'm just going to go with a 4K7 resistor. I don't think that's like a 1-for-1 match, but good enough, I guess. Because I don't think that this circuit like depends on you using the exact values. All right, 4K7 resistor to ground. Like so. And then, okay, we have the 680K that connects both ends together. I don't think I have those, and I don't think that we, like with our caps, I don't think we need 680. I think ours should be, again, I think it should be bigger, right? Because the cap, a bigger cap fills up slower, and so if you want to have the same functioning with a smaller cap, we should use a bigger resistor because that should slow down the rate at which it fills up. So the next best thing they have is a 1 meg. So let's try it with a 1 meg. So yeah, connecting the other ends of the caps together with the resistor, and then we want to connect this end. It doesn't really matter; it's symmetrical, right? So we should connect one end to the output and one end to the inverting input. Let me see if I can find a jumper that actually fits. Well, not that one. Maybe this one. Yep, that leads to the inverting input. That's perfect. Oh yeah, right. In case you don't know, like for these chips, you can always just look up the pinouts, called the pinout. You can just look up the TL074 pinout, and you're going to see like what the configuration is for the pins. You know, at some point you're going to know it by heart. So the second pin, you know, so you start counting from here. The second pin is always the inverting input. The third one is the non-inverting input, and the first one is always going to be the output. So in our case, we have now connected this side of our two capacitors to the inverting input. So we want to connect the other side to the output. Let me find a matching jumper. I don't know why I find that so satisfying. It would be so much easier to just like take a super long jumper and just like, you know, put it in there. But I don't know. I like this. All right. That should, in theory, be everything. Now we want to, if you want to listen to it, we should pick up the signal from the output. I am going to put a resistor in there because I am going to connect this to my interface. I don't want to kill it. So let's put a big resistor in there. is going to be 100K. That I'm going to put over here, nice and far away from the action. And then I am going to set up a very improvised output jack socket. Yeah, I really would like to have like some setup where I don't have to like resort to this kind of stuff, but so far no luck. All right, and then this I'm going to connect straight to my interface. Boom. And now we need a trigger. So I think that we can probably really get away with using a switch. I think we'll have to divide down the voltage that we feed through it, but I think it should be okay. Probably, maybe we get some issues because obviously not debounced, but let's see. So this is the switch I'm going to use. This is a very simple, like I think these are called momentary switch. So momentary switches. So you click it and it makes a connection, right? As long as I hold it down, it's going to make a connection. All right. And I said that I don't want to just feed it straight like 12 volts because I assume that then the output volume will be very high. It's probably going to be distorted. So we want to use a voltage divider and divide down the voltage before we then feed it into the trigger input. All right, so let me do some calculation in my head. So we have 12 volts up here. We want to feed it about 1 volt, so we want to scale it down by a factor of 10. So if we go with 100K, or maybe even less. So maybe let's try 100K and 4K7, just because I have them lying around here. That should put us in the ballpark, I guess. All right. Now I kind of navigated myself into a corner here because there's no space up here that I could use to set up the switch. So I'm going to have to do it up here. Like so. All right, so if we now take this, okay, let's imagine that we have a jumper here, then we would put the 4K7 in here. This should give us our voltage divider, as soon as it connects, of course. Boom. Okay, so now at this point here, we're going to have around, I don't know, 800 millivolts, 700 millivolts, something like that. And now what we want to do is we want to install a pull-down resistor at the op-amp's non-inverting input, which is our trigger input. That will be here. Now, why do we need the pull-down resistor? Well, because since we're using this this switch, which as long as it's not pressed, it does not make a connection. The issue is if it doesn't make a connection, then there's no defined voltage at our trigger input, right? But we always want to have a defined voltage because otherwise you can get issues with like noise and, you know, like RF signals going into your chip and whatever. So we just want to make sure that the thing only triggers if we want it to trigger, right? So we pull it down to 0 volts, and only when we push the button we will see like a voltage above 0 volts at the input. Now I just realized that this is obviously gonna influence like the total like by how much we divide down the voltage, but it's probably, I don't know if it's negligible. Let's see. Okay. I'm going to put in the switch over here. And now we need to get the voltage from here, and we need to feed it into the non-inverting input. That's not it. Let's see. Almost. I think then it might be this guy. All right, That seems good to me. Okay, so voltage divider goes into the switch, and then the switch goes over here to the non-inverting input. We have pull down resistor over here, oh, wait a second, can't we just do the following? Can't we just say, I mean, this is not crucial, but can we just say that we use the 4K7 as the pull down resistor? Right, because then, as long as we don't push the button, this is pulled down to 0 volts. If we push the button, then the voltage divider forms, and we get our voltage that we wanted. I think that's probably more efficient. Again, that's not crucial that you do that, but yeah, I think that's nice. All right, let's see. Let's see what happens. I'm going to turn this volume very much down because I don't want to hurt your ears. All right, let's see. It didn't blow up. My power supply has like a current limit, so like an overcurrent protection. So if there was a short, it would have already shut down, which I find very like reassuring. All right, moment of truth. Let's see. Let's turn this up. Okay, it's just clicking. Maybe I made a mistake somewhere. Let's turn this off. Well, we got the op amp. We've set up our capacitors over here. We have connected both ends together with a 1 mega ohm resistor. Oh, this one is incorrect. This one is incorrect. See? Boom, it has to go over here. All right. Good. Let's see if I made any other mistakes. So the middle is connected to ground through our 4K7 resistor. And then the one side is connected to the inverting input. The other side is connected to the output. Trigger goes into the non-inverting input. And we heard the trigger, so that seems to be fine. So I hope now it's working. Let's see. Oh yeah, that sounded good already. Oh. All right, so yeah, you can hear like what was discussed in the chat before, right? So this button is not debounced. So I press it once, but we get a bunch of hits. Oh, very fast. Okay, but yeah, sounds great, no? Let me turn it up a bit. Okay, that's probably a bit too high for a kick, right? That almost sounds more like a tom. So as we saw before, what we can try is we can try to increase the value of this resistor to see if that gets us more in the ballpark of what we're looking for. Let me see if I have a 10K somewhere. So yeah, my gut feeling is that a 10K is probably gonna be about right. But then I'm also curious about what happens if we change the value of this resistor, right? So we might have to like bust out a potentiometer to be able to do more conclusive testing here. All right, but first of all, we're going to replace the 4K7 with a 10K. This guy. All right. Okay, let's see. Yep. That's better. It's now it's distorting because I've turned up the input. Okay, so it for my taste it decays too quickly, right? Like it's like a very quick little hit. And then it's gone. So I have a gut feeling that it might have to do with the other resistor. So I'm gonna to try and verify that, I'm just gonna try and replace that with a 470K instead of a 1 mega ohm. that should be like a big enough difference to be able to see like which direction it's going in, right? Because that's like, I always find that helpful. Like if I have questions like these, like, you know, which component values do what to the circuit, it's always like very helpful to just identify like a direction at least. So my assumption is that probably the resistor here will influence the pitch as well. As I said earlier, it's probably gonna speed up the charging process of the second capacitor. Oh no, that was the wrong resistor. And yeah, probably it's also gonna increase. Oh no, I should switch this off. It's also gonna probably increase, like, it's gonna make it quicker, like even quicker, I think. So if this is true, if it does make it quicker, then we might consider increasing the capacitor sizes. Yes. Okay, that's much quicker. All right, that's not what I was looking for. I wanted it to be longer, actually. So let's put the 1 meg back in. Oh God. All right. Okay, I think it's a bit longer, and obviously it's also lower in pitch. But now let's try and increase the value of this of these capacitors. So I'm gonna go really extreme. I'm gonna switch them out for 100 nanofarad caps. These guys here, and I assume that it's going to make the pitch much lower, and probably it's also going to make it oscillate for longer. But yeah, so I assume, like, in this very simplistic circuit, the pitch and the decay time is just tied together. Like, I'm not sure if you can actually influence the decay time independently of the frequency. But yeah, let's try this. Yeah. Okay. Though I'm not even sure if it does decay slower. So it's just like a quick hit and then it's gone, right? There's not much length to that. I'm gonna check the chat for a second. All right, James says F0, I'm guessing that's frequency, and decay are interdependent. Martin asks, why not try original values? The problem is I don't have 52 nanofarad capacitors. So I had to like improvise with those. So I improvised with the resistor values. So I can't go to those values, unfortunately. All right, Drunkard says bigger caps, better fun. That's true. Dean asks, is the plan to go through all the instruments? Eventually, not in this stream. Eventually, like this is going to be a multi-part series, basically. All right. Any other questions or suggestions? How would changing the value of the other resistor, the one that's in parallel with the caps, in the feedback loop affect our output? We already saw this. Like I exchanged this for 470K, and we saw that the pitch went up and the decay went down. So I think all of the values are just going to affect the pitch, and the pitch is also going to affect the decay. So it's all kind of like just tangled together. I think maybe we could try making this asymmetrical, right? Like using a different value cap on the one side and a different value cap on the other, like two different value caps on both sides. That's what we could try. All right, let me try that. Let me take out one of the two. I'm going to go with the one that's connected to the output. Switch this for 33 nanofarad. And then keep the other one at 100. And then we're going to see what that does. Boom. All right. Oh. It just like severely drops the frequency. Interesting. All right. Let's try it like so. Now it's like turned around, right? 100 nanofarad here, 33 here. Let's see. Okay. The opposite. Super short. And not much oscillation. Yeah, someone just said in the chat, caps need to be the same for resonance. I mean, we just saw that it's probably not true, right? Like if the one at the output is smaller than the one at the non-inverting input, or at the inverting input, sorry, it still seems to work, right? The frequency is very low, but it does seem to work. It's very bassy. All right, Dean asks, could we use caps in parallel to achieve the capacitance used in the original schematic? We could. I am not sure. How to calculate that. Let me check this. If we can find a calculator. Do they simply add together? Is that how it works? Capacitance. Wait, let me switch over here so you can see this. So I'm going to go in the browser. I'm going to Google this. Capacitance in series. When capacitors are connected one after another, they are said to be in series. For capacitance in series, total capacitance can be found by adding. Oh, Jesus Christ. In parallel. I think that's easier. When capacitors are placed in parallel with another, total capacity is simply the sum. All right, so that's true. All right, so for 52, I have 33, and I also have. Wait, now I'm thinking if that even makes so much sense. I mean, to me, it's like, okay, so we understand the basic functioning of this, right? So the question now would be, what will we gain if we get the exact values right? I'm not sure if that's super helpful. If you still really want to do that, let me know. But I'm not really thinking that that's like very interesting. So let me know. I think, oh, somebody asked, could we have a catch-up for us late journalists, please? Yes, I think we can have a catch-up, because the next thing that I want to do is like go back to the schematic, look at what we've done right now, and then look at the next section that's like in the schematic, which should be interesting, and maybe that's actually used to simulate a longer decay. So let's switch over here. For anyone that's new or has joined recently, basically what you see here, first of all, it has ugly black bars on the side because my pad has a different aspect ratio than my stream. So stupid, sorry. But yeah, what you're looking at here is the original TR-606 schematic from the service manual, which was provided with the drum machine for you to make repairs or whatever yourself. So this is the original, like from Roland. This is officially like the schematic, and we are currently looking at the bass drum part of it, because the bass drum seems to be the simplest of the 6 voices that are part of this drum machine. And what we've done is, first of all, we have looked at the trigger input. The trigger input is basically all of this. This circuit is a little bit more complicated because the drum machine is using a single-sided power supply, and so these op amps they don't have negative voltages. They have ground and they have 15 volts. And the issue with that is that they needed to take the trigger, like this bass drum trigger here, and they needed to bias it upwards. So that, along with buffering, is what they do in this kind of section. And what we just set up on the breadboard basically is this part here, which doesn't look like a lot, but that's actually the heart of the entire thing. And basically what it does is it generates the actual sound that you hear, like the bass drum sound that you hear come out of the drum machine. And the way that it works, this is where I struggle at the moment. Like I'm not entirely sure I can explain it well. I just have, or we just saw in the simulator basically like the basic way of functioning. So the idea is that whenever a trigger goes into the op amp over here, then this causes it to increase its output voltage, and this charges up, for one, this capacitor and also this capacitor over here. This cap up here charges very quickly, this cap here charges very slowly. And so the voltage at this node, at the inverting input, also rises very slowly. And then because the trigger coming in here is a trigger, like it quickly drops again. And once the trigger drops here, the op amp's output will go negative, so like this. And this will drain this capacitor quickly, and this capacitor up here slowly, right? And as I said, I haven't completely understood the mechanics behind it, but basically what happens is that the whole system gets in this state of kind of like a seesaw, like it's kind of like wiggling back and forth, like because this cap is draining, or this cap is like kind of responding quickly to changes in output volume, and this cap is responding slowly to changes in output volume. You get a situation where like they kind of bounce back and forth. That's like the best I can do right now. Like eventually, like when I've thought about it more, I'm going to do a proper video on it, but that's roughly like what's happening. And the resistor here and also the resistor up here, they are important for the pitch of the oscillation, basically. So if the resistor values are bigger, then you get a slower oscillation, so a lower pitch. If the resistors are smaller, you get a quicker oscillation and a higher pitch. And also the thing here is that pitch and kind of decay time are tied together. Because this oscillation like dies down over time. Like this is not a self-sustaining oscillation. This is an oscillation that's kind of like triggered, and then it kind of like decays in, I think, in frequency and in volume. Yes, and so we've just set all this up on the breadboard. We've tested it, and it does make a satisfying thumping noise. But to me, like the decay is a bit too quick. And now I'm basically wondering, okay, so if we, like in the beginning, we listened to the actual drum machine and we saw that the kick is actually not as short as the one that we just heard on the breadboard. By the way, on the breadboard, we could ditch this entire kind of triggering section. Because for one, we don't need to bias anything up because we're driving our op amp just with a dual power supply, so no need for that. And also, like for now, we don't need the buffer and all of the stuff. So we just omitted this basically. All right. So what I'm thinking now is that this thing probably sounds like in the drum machine itself probably sounds very close to what we have. Yes, we don't. Or I don't have these exact capacitor values, so there's going to be some difference, but I don't think it's going to be big. All right, so now the question is, how do they make it sound longer? How do they extend the decay? And I think the key here is probably this second op amp, right? And if we look at this, we can see, for one, that the capacitors are much smaller and the resistor down here is bigger and the resistor up here is smaller. And I think I was wrong. I think this thing is actually just providing like a clicking, right? Because we saw if the capacitors are smaller, they get charged up quicker and they also get drained quicker. And so the frequency of the oscillation is going to be much higher, right? Because this is 15 nanofarads versus 56. So yes, I think this thing here is adding the click and this thing here is adding the thump. So maybe I'm wrong. Maybe it's really about just the fine-tuned values that make it have the exact length that it has in the drum machine. But yes, so my assumption is this is the bass and this is the snap. Nevertheless, let's try and set up the second one too, and let's see how that sounds together, right? Because yeah, as you can see, or as we also discussed earlier, these two outputs, they are mixed together, right? Here and here. We can see that both are AC coupled over here, so they're being routed through capacitors. And then also this seems to be, oh, this is confusing, right? Because if it was just a resistor followed by a cap to ground, we would know it's a low pass filter, but there's also like these series capacitors. So there is, wait a second, these appear to be 1 microfarad. So they should not affect the sound too much. So I'm guessing that they are like kind of just jamming AC coupling and then some light low pass filtering together into kind of the same thing. And then they have the potentiometer here, which is basically just a volume. Yeah, that's the bass drum level. That's the volume control. All right, so I am going to set up this separate tone generator, and then we're going to mix them together like shown here, and we're going to see how it sounds. All right, let's go to the breadboard again. I'm quickly going to check the chat. All right, Buck says that's a drum beater, probably it should be shorter. Yes, I think it's higher pitched and shorter. It's the transient of the bass drum, correct. All right. The first op-amp is providing the hit of the drum, the second the fading sign. I think the first one is actually the fading sign. I think the second one is the hit. But we're going to see. You could use pots for the resistors to check combinatory effects. Yes, we're going to do that in a second. All right, let's go ahead and do that. Oh, another question. It would be nice to see the waveforms from the breadboard on the oscilloscope. Is that possible? It's gonna be a bit difficult with the setup that I have here. I do have a USB oscilloscope, so I should be able to stream it on the computer. But for now, I would suggest we set up the second op-amp. We see how that thing sounds. My assumption is it's gonna be the click, and then we are going to mix them together, and we're going to see how it sounds. All right, and yeah, the squid, the first sound generator. Yes, I'm gonna switch over just for you. So we basically, what we did right now is we set up this. I don't even know what to call it. Oscillator. Whatever. We set that up. We listened to it. I can show it to you right now. It sounds quite thumpy and nice. Let me exchange these capacitors. Boom. So as I said a couple times, I don't have the actual values that they use. I don't have a 56 nanofarads capacitor. So I am substituting with a 33. And it sounds like this. Maybe I can turn this up a little bit. Right, and I think maybe that's actually what the drum machine sounds like from the length of the decay. I think we're not that far off. All right, so let's set up the other op-amp. So here, actually I have the correct values. Because we want to use 15 nanofarads, and thankfully I have those. And then let me look at the resistors. So we need a 12K. That could be difficult. I think maybe I think I have 14Ks. All right. So 15 nanofarads first. I'm just going to mirror the setup that I have here, basically. Just because I'm lazy and it's easy. So this one in here. Put the other one up here. Boom. Okay, and then we are going to need a jumper. What I hate about these jumper boxes, I mean, I love these jumper boxes with these like pre-lengthened and pre-bent jumpers. But the horrible thing is that like a bunch of them are super important, like this length and this length, and so I have to use them all the time, but they just disappear because I use them so much, and they just like fall off the table, and then they end up in the vacuum cleaner, whatever. And so I always end up in a situation where I have to like completely just like scour to find any correctly what's the word? Any jumpers of the correct length. But there's an abundance of like ones that I never touch. And that's just really frustrating. All right, let me see. 12K we're looking for. I have 10K. That could be a substitute. 9K, probably not that good. 14. I think these are 14s. They might not be. So I have to bust out my my multimeter. Give me a second. All right, let's see. So that's the problem. Like normally I like to buy my resistors like in these packs because they're like nicely labeled. It's like 100 of them, and if I lose some, it's fine. But some resistors, I kind of figure like, oh, I'm not gonna need a lot of these, so I just buy like one-offs, and then I don't label them. And then I have to just like rely on my multimeter, and I really hate that because it just slows you down. All right. If this one that I'm testing right now is not a 14K, then I think, oh, it is a 14K. It's actually 13.6, so that's actually not even closer than I thought. All right, so we want to go from the center here to ground. That's good. And then the next thing is, I think, a 560K. And I think that's going to be the same issue that I just had. Because I vaguely remember like having one of those in some build. But it would be unlabeled. 360K. 270K. You know what? I think we're just going to go for a 470K again. Just because that's easy. Where's the pack? Here's the pack. All right. So 470K. I don't think it, I mean, it's close enough. It's like, I mean, yeah, it's 100K, but like in the grand scheme of things, I think it's similar enough. All right, put that in there. And then we need another white jumper to connect the other side to the inverting input. Oh, here it doesn't fit. That's interesting. Is it a different kind of jumper that's also white? That's annoying. That's really annoying. So yeah, never mix different types of jumpers, I guess. All right, that works. boom, put that in there. And then we're almost done, I guess. So now we just need to get our... Okay, now with the divider, it's going to be problematic because if I do the same setup, so what I've done here is like I've implemented a voltage divider that runs just through this button. So whenever you push the button, you get like a bit less than a volt at this point. Now I could just also route it from here to this op-amp non-inverting input and put a 4K7 to ground, but then we have two 4K7 to grounds, and so then the trigger is going to be reduced in volume, so I think I'm just going to replace this with a 10K and then also do a 10K on the other side, and then we should be okay, right? Because resistors in parallel, yeah, I think two 10Ks in parallel is like roughly similar to one 5K alone. So let's see. 10K over here. And then a 10K on the other side, like so. And, oh, come on. That didn't work. Let's try again. All right. And then we need a jumper to go from the button to the other side, like so. Oh my god. Okay. And then we just need a blue jumper and then we're done. Okay. And then we also need a resistor between the output up here and our output socket, simply because I don't want to fry my audio interface. So, and I'm expecting that the oscillation is actually relatively powerful. So we'll do it like this. Okay, so a moment of truth. Let's see how this sounds. Yes, as expected, we get a high-pitched kind of initial clicking sound impact. Okay, so now if we, I think we can even make our lives very easy. I think we could just connect these two together via the 100K resistors, right? We could just say, all right, so this thing here also connects to the output. And this should give us a crude kind of mix of the two. Let's see. Oh, that sounds pretty good, I would say. Let's remove the high-pitched part. Doesn't seem to be adding like a lot, no? Oh no, it is. All right, I think that's pretty close, no? Let me check. What do you think? All right, you're talking about Radio Shack. All right, fine. Then I'll just keep going here. So I think it's pretty close, but let's not assume. Let's try it out. So I think, unfortunately, because my interface only has it only has two inputs, so I cannot set up the 606 at the same time as our circuit here. But just to get a rough comparison, oh god, I'm sorry. Oh yeah, you hear this is broken. I'll turn down all the other sounds, and we're gonna just listen to the bass drum, and we're gonna see how it sounds. All right, let me do a 4 on the floor, like so. So as I said before, this thing is horribly in horrible shape. So you can hear all kinds of like background noises. But I think I was right earlier. I don't think that the decay here is really longer than what we hear in our circuit, right? This is also just like a very, very quick little snap, and then it's gone. So if we compare this to our version of it again. Whoops, I'm sorry. I think that's very close. No? I think that's very close. All right. Now what do we do? Okay, let me check the chat for a second. Viva la revolution, yeah. Cap on the command output signal is a simple filter. Yes, I think the high pass probably like in the original design filters out a little bit of the initial like clicky transient. That would be a good idea. All right. The volume knob is dead. Yes, the volume knob is really dead. I think the potentiometer needs to be replaced actually. George asks, how much does the 606 cost today? So I bought mine, I think like 5 years ago for 450, something like that. And I mean, back then I was still in university, so it was an insane amount of money. And I don't think I would pay that again because the state is really horrible. So I mean, as a collector's item, it's cool. But yeah, I think I would need to get it fixed up for it to be like valuable again, to me at least. Yours sounds better. Yes, I mean this circuit sounds better obviously because it's not gone to hell yet, I think. All right. What else? You can hear, Buck, what did you say? I didn't see it. You can hear the combination of the short beta oscillator and the thumb. I don't know if you're referring to my circuit or the 606, but all right. What else? Replace the button with the signal generator. Yeah, that would be interesting. Feels like it's missing some low end. Yeah, we can probably fix that by tweaking the values here. Probably if we increase this resistor size a little bit, I guess. Now if we run it through 4 fuzz pedals and take over the Dutch clubs in the 90s, yes, probably could do that. All right. So what do we do now? The low pass filter at the output seems like, I mean, yeah, we can anticipate what's going to happen, right? If we put a low pass filter after this, it's going to sound less clicky, but I'm not sure if that's actually so interesting. What was the other suggestion, like feeding it a signal, like a trigger input? Well, I mean, then we could sequence it, but I'm not sure if that's like super interesting. So let me bring up the schematic again to just see what we have. Whoops, shut itself off. All right, so let's see what else we have here, like what we could tackle like in the little time that we have left. So I think it's not really all that interesting to try and replicate the trigger input because we don't really need it in our setup. For us, just like a buffer and then a high pass filter would be enough. So I don't think there's much use in building this. The output volume, I mean, it's trivial. It's just a potentiometer. The low pass, as I said, like we all know what's going to happen. So I think we can leave that out for now. Maybe I thought maybe if the tom wasn't too different, because I thought that maybe the tom is just like a variation on the bass drum, but it does look much more complex to me. All right, so then I think what we're going to do in the last minutes is I am going to set up a potentiometer here just so that we can see, you know, like the extent to which that has an effect, like if we dial in more or less resistance. But I'm not gonna simply straight up replace it with a pot, or maybe I can. I was just worried about, like, if this was just like a plain potentiometer, then this, at the minimum setting, this would be a short circuit, but I don't think we really care because, you know, there's a capacitor in the way, so it's fine. All right, so I think I'm going to replace this guy here with a, let's say with a 20K, with a 20K potentiometer. And then we can experiment. Maybe that's actually maybe that's actually not enough, right? Because we don't actually have a 3K3 here right now. I think I replaced it with a 10K. So maybe I will go up to something like, let's see what I have. Maybe I have something like a, maybe I have something like a 50K. I think that would be cool. 100. Oh God, I hate this already. Oh no, these are all just gonna be fucking 100Ks. 100K. Another 100K. Another 100K. You know, what I really want is, I've seen, like, on this website, I've seen this super cool, it's like one of these cabinets that you see like at the electronics stores, where it's like you can spin it around itself, and it just has like all these little drawers, and you can, it's way too big for me, so it looks like you can fit like an entire store's inventory in there, but it looks super cool. And I imagine if just all of the little drawers were like properly labeled, then it would be like a huge help in situations like these where I'm looking for a specific type of potentiometer. All right, so no 50K, but I did find a 20K. And I think what we can just do is we can set up a 4K7 as the baseline here. And then we add the 20K to it, basically. So in total, we're going to be able to go up to 25K and down to 4K7, obviously. And I think that should give us like a decent feeling for how the resistance impacts the sound. All right. So we're going to pick up our signal from here, from the middle, between the two caps. We're going to route it over here, in a very ugly way. And then, since we are just going to use this as a variable voltage divider, we simply set up a connection to ground from this point over here. And now if I put my pot in here, then if I turn it all the way to the right, we have the minimum setting, which should give us the highest pitch, so it does make sense, right? Pitch high is to the right, and then if I turn it all the way to the left, then the resistance is going to be very, very big, and so the pitch is going to go down, right? So we have low pitch, high pitch. That's how it hopefully is going to work. Let's see. So let's start out with a very high pitch. Oops. Yeah, as expected, high. Let's turn it down. Oh, I've made a mistake. Yes, I've made a mistake. All right, interesting. I put this in the wrong slot. I put it into this one when it should have been this one. Boom. Put it in here. And there. And now. This is not on, by the way. Like, the power supply is currently off. I'm not sure why it still makes all these noises. All right. Let's see. Let's turn this up. Okay. High pitched. That almost could pass for a tom, no? I mean, it's not, obviously it's not a match for the 606. Like the 606 toms, like they have like this really weird quality to them. Like it almost sounds like there's like this echo or like this weird tail to them. I don't know. I mean, this is This could be serviceable as like a conga or whatever. All right, let's turn this down. Yes, as expected. So at the maximum setting, very, very low pitch. But obviously we still get the click from the other oscillator. So the click is still there, and then the very, very low oscillation, right? Turn this up, and we get more of a usable pitch, right? It's actually not so bad for a range. Like, I think maybe this is like going down too low. I don't think this is usable anymore. So probably this could be like a 10K, and then that would be a good range, I guess. All right, so I feel like that's a good place to leave it, unless you have any questions. So I guess I'm going to dedicate a few minutes now to questions, or maybe you have more suggestions what we could do with the circuit. I feel like this is a good place to leave it. All right. So Barbarossa says the 606 toms have pink noise mixed in for that fake reverb effect. Ah, that's what it is. Yeah, that makes sense. Like I always thought like it's some kind of noise, but it didn't sound like white noise because it's like too muted for it. But pink noise makes perfect sense. Okay, Buck says that gets really rich with the higher frequencies. Is that with the lower resistance or higher? Gets really rich with the higher frequencies. I'm not sure what you mean. Let me try it again. And oh, James says a diode would stop the double trigger. That is probably true. Let me get a diode. It's not necessary, but I want to do it. So I think we have to wait, I'm not entirely sure. I think a diode pointing upwards from ground, is that it? Is that how it works? No. But wait, why does it sound in the other direction? That's interesting, no? So electricity, I push, electricity flows through, voltage goes high, that triggers it, and then if I take my finger off the button, it should just go down to 0 volts, but still it triggers. So I'm not even sure why that happens. Or maybe if we do put a diode just like in here, we replace like this jumper with the diode, like so. And then we put in another diode over here. Maybe that does it. Let's see. Boom. No, same thing. That's the same. Oh, what's that? Okay. Anyways, it doesn't work. But yeah, Buck, let me know what you meant here. So this is with a very low resistance, and then this is with a very high resistance. Right? So higher resistance, lower pitch, and then lower resistance, higher pitch. All right, more questions. All right, so question from James was, a diode would stop the double trigger. As we just saw, it does not. So I'm not entirely sure how we could fix that. VHS asks, is this video going to stay up on your channel? Yes, but the live streams are kind of reserved for patrons. So they're going to be taken private, and you can only view them if you have the link, and that's going to be on Patreon. Martin asks, do you plan to create a kick module? Probably eventually at some point, but only if I can do something interesting with it. Like I would not just take this and be like, hey, this is my kick module, right? Because this is a very basic circuit. It doesn't sound bad, but I don't think that's very interesting. So I would want to like find some way to make it cool, and then maybe. Okay, Lars and me builds have enjoyed it and want me to keep it up. I'm going to do that. So the plan is that I'm just going to do more streams in this exact format, looking at the other voices. So I'm assuming next time probably we're going to tackle like the toms, because those seem to be like just building on top of the kick and then adding some noise and whatever. So I think that's an interesting way to continue it. HRH Crab says, no questions, but thanks. As a 606 owner who absolutely loved the machine, this was really interesting. Cool. Thanks. I'm very glad to hear that. Buck says, now I want to try this with 3 caps and put the pot wiper to ground and the other 2 legs between each cap. It sounds very adventurous. Sounds very good. Try it and let me know how it went. Double trigger is because there's no integrating cap. C26, or was it C25? Let's look at the schematic again. 26, 25. 26, 25. This thing here is what you're talking about. That would be a high pass here. Yeah, maybe that's the reason why. Though, I mean, if you get a trigger here and then you get a spike here, and if this goes low, then you get a negative spike over here, right? So maybe, I'm not sure if that would double trigger. I mean, obviously it doesn't, because the 606 doesn't double trigger. So I guess that's not a problem. So yeah, maybe the high pass is what fixes it. Rascal says, classic. I love finding music by people outside the electronic music world who made music on 303s for cost convenience reasons, and then resampling the recordings into acid tracks. That's very devious. All right, what else do we have? All right. A lot of people that liked it. I'm very happy to hear that. Matthew says, I would recommend a TC1 component tester to help with sorting all those loose unlabeled components. Super cheap, but makes a massive difference. Appreciate everything you do. Thank you. I've never heard of a TC1 component tester, but I will look it up. This is a good tip, I guess. Okay, Buck, for you it was more resistance, so lower pitch. So that to you made the high end more crisp, if I got this correctly. If so, cool. Atsky says, stock up on proper valued caps for the next stream to eliminate uncertainty with more complex blocks of the design. That's a very good tip. I'm going to do that. I'm going to make sure that I have all the component values. Then we can have, hopefully, like a one-to-one match. Fuzzy Music says, the trigger pulse shape is very essential in how the drum will sound. Roland is very specific about this in the 808 service notes. All right, that's also a good notice. In this setup that we looked at here, this one, I'm gonna make a bold kind of assumption. I think that the only thing that really influences the shape of it is probably just like the high pass here. That's what I think, at least. So yeah, I guess if we slapped on a high pass onto our design, maybe make a difference. Maybe we can try that in a second. But I'm going to try and go through all the other replies first. Kevin says, well, it's triggering with a change of input, so maybe a switching latch would be better. Yes, we're going to try it with a high pass first, or we're going to try it with a high pass now, and then next time maybe we're going to do something like latching or whatever. Tim asks, when will you stream next? So I aim to make this a regular thing. I think every other weekend I want to do it. So Sunday in 2 weeks would then be the next one. Top Quark says, I have a bowl full of used cut resistors. Don't want to throw them out, but it does reach a point where the value proposition of keeping them is just not worth it. Yes, I know that. I have like one drawer in my cabin my cabinet that it's just unlabeled, just loose resistors. And I always put, like, I know that I should just sit down for an hour and just like test all of them, but then I also think, okay, an hour of my time could be used in a more interesting way, so I just don't do it. So yeah, stuck in the same dilemma. Buck says, interesting, use the rest of those op amps to duplicate the circuit and get that cool chorus effect. Would it be a chorus? Like, we need like a tiny delay for it, right? For it to be a chorus. So maybe if you delay the trigger a little bit, maybe that could work. Kevin asks, it triggers again because it jumps from 1 volt to 0 volts, right? I assume so. I'm not entirely sure, to be honest. Chibik says, you can also add feedback and get 808 like resonance. Feedback in the, what do you mean? Like in the bridge T network? You would have to spell it out for me. I don't know how exactly you would do that. All right, more questions. Cowbell last. Well, I mean, on the 606, we don't have a cowbell, so that has to wait until we get to the 808. Am I keeping the streams to a Sunday? Yes, I plan on doing that because during the week I have to work, so that's not good. And Saturdays, to me, Saturday night feels like people might be wanting to do other stuff, so Sunday seems good. If you have a different opinion, let me know. Reinhard asks, can you replace the 1 amp resistor with a 2 amp for a longer decay? I mean, maybe that's how it works. No, I mean, we saw earlier that it does influence the pitch also, so we could give that a try in a second. All right, what else? Filter at the original trigger stage works as filter debounce. Yeah, that's what we want to find out in a second. What else? More questions. Are you planning to do any workshops in the future? Yes. So I am currently looking for venues here in Berlin where I could do workshops. And I am starting to talk to different stores, and I'm trying to like figure something out. I'm going to announce it when it's time. Ideally, I also would want to do it like regularly or relatively regularly. Also, I will try and see if I can get into like if I can get a workshop slot at Superbooth. I haven't talked to them yet, so you know, just from my side, that's the idea. I'm gonna try and see. Anything else? Anyone played around with germanium transistors? I've never held one, so I have no idea. Anything else? Tried the high pass in Felstad. It's a perfect word in there, but it did seem to eliminate the double. All right, so instead of going through all the questions, here's what I'm gonna do. I'm just gonna do one last thing, and I'm going to try to set up the high pass filter to see if it actually does eliminate the double, and maybe I think it's true that probably it will kind of change the characteristics of the sound. Now the question is, what's the best way to go about it, right? Because we have this situation where we divide the voltage down, and then we have like these two, like we have this kind of like 3-part voltage divider, which is a bit awkward. So I think what I am going to do is I am going to all right, I think I have an idea. So I am going to do it very quick and dirty. So we get our voltage from up here, right? This is connected to the positive rail. We have our button over here, and I think what I'm just going to do is I'm just going to take like a very small cap. Let me get something like a 2N2. I think that should be plenty. I mean, in the original design they use a 470. Right? Let's just go with this one. Let's see what happens. So 2N2, goes in here. Over here, I'm gonna remove these diodes again because I have the feeling that they're gonna maybe mess with how it sounds. So put the jumpers back in here and then also up here. Boom. And then I'm simply going to put the button in here. Oh God. And I'm actually like, this is always confusing. Like to me, if it was just a high pass filter, it's like easy to predict what's going to happen. This is now very, very strange because you have the resistor up here that goes into the capacitor, and then after the capacitor we have like the resistors to ground. Or maybe I could just move them. Could I? No, I can't move them ahead because you need the resistance to ground after the cap to actually get the high pass filtering. So let's just see what this does. All right, this this allows us to trigger it once and then never again. That's not a good feature. All right, so you know, the issue is we don't want to just simply blast it with 12 volts. That's a bad idea, right? So but we also I think we can just divide it. Can we just divide it down and then feed it into the? Maybe I'll just try that, right? So, but then we need after the cap we need the resistor to ground. That's annoying as hell. All right. So and I don't want to set up a buffer right now. That's annoying. Let me check if anyone in the chat has any ideas. You need resistor to pull cap to ground. Yeah, that's true. On the other side, so we do need the resistors here. I think that's kind of undisputed. But then the issue is, well, maybe let's just say fuck it, and we're just gonna. We need to pull it to ground on this side. Yeah, you're right. That's true. All right, so let me try and do that. I'm gonna just put this in here. And then we're going to see what happens. Okay, we still get the double trigger. Interesting. All right. Maybe if I replace this just with a straight connection to the power rail. And if that doesn't work, I think that I'm going to call it a day for today. And I'm going to come back next time with more knowledge. Boom. Okay, so it's still double triggers, even though we do have the cap in the middle. And I think also it doesn't sound really good. So yeah, didn't work. Experiment failed. So we are going to do this next time. All right, I'm going to end it here. I'm very glad you all joined. I'm very glad to hear that you enjoyed it. I hope you learned something. I hope it was interesting. And as I said, next stream is going to be in 2 weeks. We're going to like refine the bass drum. And then after we've refined the bass drum, we are going to go ahead and look at the toms. And that's it. Thank you so much for watching. And until next time, see ya.